So we've been learning about rates, rate laws, rate constants, etc. And what we've talked about so far has been something happening at a constant temperature. And we mention that because the rates of chemical reactions are sometimes highly sensitive to temperature. An example is a 10 degrees Celsius increase in temperature can double or triple the rate of a typical biological reaction. And that's one of the reasons your body regulates its temperature so tightly, is to keep the rates of those biological reactions where they're supposed to be. So the rate constant is a constant, but it's only constant if the temperature remains the same, which is why we saw at least one example where it told us what temperature the thing was happening at, even though we didn't need to know. But we need to know that it was at a constant temperature. So the temperature dependence of the rate reaction is in the rate constant. And rate constants generally increase with temperature, but that's not always the case. So the relationship between rate constant and temperature is shown in the Arrhenius equation. So here we have our rate constant is equal to a frequency factor times an exponential factor. So that's e raised to the power of negative EA over RT. EA is our activation energy, and R is the gas constant with units of joules per mole Kelvin. T is the temperature in Kelvin. So what is an activation energy? What is a frequency factor? So you learned in Chem 1A about exothermic, endothermic reactions, etc. And so here we have an energy diagram for an exothermic reaction. The reactants have a higher energy than the products. Where does that energy go? It goes into the surroundings, right? So you would think, well, this reaction is just going to go spontaneously at any time. But there's this barrier called an activation energy. And the reaction or the reactants have to have enough energy to get over that barrier before the reaction can occur. So that's the activation energy, is this hump of energy here. And then the frequency factor is the number of times the reactants approach the barrier per unit time, usually per second. I don't have a better analogy than miniature golf. So this kind of looks like a miniature golf course to me. So here if you got your person holding their golf club, whoops, there's the golf club, right? And here's the ball. And there's all of those humps and stuff, right? And you have to hit the ball with enough energy to get it over the hump. And some of them, you have to hit it a lot harder than you think. So you hit it once and it kind of goes up halfway and it rolls back. That was one approach. You hit it again, it doesn't go over. That's 2 approaches. So the frequency factor is how many approaches to the barrier the reaction has, say, per second. So let's think about a simple reaction. Here we have methyl isonitrile, and it spontaneously can rearrange to form acetonitrile. This is kind of a weird reaction, because what happens is this N with a triple bond to C, this piece can just sort of swing around. So here we have the blue and the black, and now the rest of it's connected to the black and the blue's on the end. You're like, okay, well, that's kind of weird. Yeah, it is kind of weird. The molecule goes through an intermediate state that has high energy. And so that's when that piece has kind of rotated half around. And so here we see more of a Lewis type structure where we can see it's kind of in between one and the other. This is known as an activated complex or a transition state. So in order for it to do this, it has to have enough energy to begin breaking the nitrogen bond with the carbon, weakening that bond. So it's like a tension on a rubber band or something. You have the energy to pull it out. It allows this group to begin to rotate. So the activation energy is the amount of energy needed to get to that state, where it could go either way now. It's like halfway. It could go back, it could go forward. The energy needed to reach the activated complex or transition state. So this is the activation energy again. If the activation energy is greater, maybe it's up here, it takes more energy to get to that state where the reaction could occur. If this is less activation energy, the hump is not as big, you don't need as much energy to get over. If we have a high activation energy, it's going to take, the reaction is going to be slower because fewer of the approaches are going to have enough energy to get over. Questions? You following that at all? So the frequency factor represents the number of approaches to the activation barrier per unit time. So that NC group approaches the activation barrier each time it begins to rotate. So it begins to rotate. If it doesn't have enough energy to fully rotate, then it just comes back down this way. So that's one approach. The frequency factor then represents the rate at which the NC group wags. So you can think of that NC group as being like a dog's tail, right? You come home, your dog's tail goes, right? Vibrates from side to side. So this NC group, you can think of it as wagging back and forth. And so the frequency factor represents the rate at which it's wagging. And some of those wags are going to have enough, sometimes the dog's tail just kind of wags a little bit, and sometimes it's like full side to side, right? That's got more energy. So those little wags are going to come up here, not have enough energy, and come back down. The big wags are going to have enough energy to twist this completely and allow the reaction to occur. That makes sense? So what about the exponential factor? Well, this gives us the fraction of molecules that have enough energy to make it over the activation barrier on a given approach. So that factor is going to be a number between 0 and 1. It's the fraction of approaches that are successful. If the frequency factor were 10 to the 9 per second, that's really, really high, right? But molecules are really, really busy little guys. Frequency factor times an exponential factor will give us our rate constant. So if this was the frequency factor and this was the exponential factor, we multiply those together, and we had a rate constant of 100 per second. That exponential factor, that is the E to the EA over RT, right? That's where the temperature dependence is. That factor depends on the temperature and on the activation energy. So if this factor is equal to 1, that means every approach is successful. Well, what would cause that to happen? If EA is low, if the activation barrier is low, and the temperature is high. Right? So how does this number become 1? There's an exponent that you can raise something to a power that is always 1, 0, right? If this piece up here becomes 0, then e to the 0 is 1. So if this gets smaller, then the exponential factor is getting closer to 1. So to make this piece smaller, activation energy has to be smaller, and or temperature has to be larger. At high activation energy and low temperature, this factor approaches zero, where no approach is successful. So if the activation energy is really high, we're not going to have as many successful approaches, right? If the temperature, see, the temperature is related to the kinetic energy of those particles, right? And so when temperature is low, everything has lower energy, and so also more of those approaches will be unsuccessful. Does that make sense? So if we look at thermal energy distribution, we learned about this in Chem 1A, temperature is a measure of the average kinetic energy of the particles in a substance, but the molecules have a range of energies. So the temperature is the average, but some are really, really slow, low energy, and some are high, and we're just looking at the average. So here in the blue at time 1, we're going to have a distribution of energies, right? So a lot of them are going to be kind of this middle area, but some of them are going to have much higher energy, and some are going to have much lower energy. And the y-axis represents the fraction of molecules with that given energy. If we increase the temperature, the average energy increases, but this distribution also spreads out. And so when that happens, the amount of, the fraction of molecules with enough energy to get over the activation barrier is going to increase. It increases more than you would think. It's not just that, we have to get the average up here. No, when we get the average closer to the activation energy, because this spreads out, we're looking at the area under the curve here. So for the blue line, the area under the curve is pretty small, but for the red line, it's much, much larger. So this is the fraction of molecules that can get over the activation barrier. Any questions? Yeah. T1 would be lower temperature. Good question. And it does show that down here, but it's probably not really obvious. So T2 is larger than T1. I only just noticed that little blue box myself. Any other questions? So this summarizes what we talked about so far. The frequency factor, the number of times that the reactants approach the activation barrier per unit time. That's the A. The exponential factor is the rest of the Arrhenius equation, and that's the fraction of approaches that are successful, meaning it gets over the activation barrier and produces products. The exponential factor will increase, get larger, as the temperature increases, but it will decrease as the activation energy increases. So they're looking at the two different things, and they're saying one is increasing and one's decreasing, and it's kind of confusing the way they say it. Because here it increases with increases and decreases with increasing. So let's just, so if, so this is the activation energy, is this part right here, right? So if we increase that, just think about, miniature golf and hitting the ball and trying to get it to go over this hump. You're not hitting it real consistently, right? Some of them don't have enough energy. Some of them you're like, ooh, I sent that one flying off the course. There's a distribution of energies. If the bump is higher, fewer of your hits are going to go over. If the bump is lower, more will go over. What if there was no bump at all? Any of your hits would go through, right? So if the activation energy is larger, then that factor is going to be smaller. Fewer of those approaches will be successful. If the temperature is higher, that means like the putt-putt golfer is like, pumped up on energy drinks or something. He's got a lot of energy hitting the balls faster, right? So then that exponential factor, the success factor, is going to be larger, okay? Okay, so let's see if we can do this one. Which statement best explains why reaction rates generally increase with increasing temperature? Reaction rates increase with increasing temperature because as temperature increases, a greater fraction of molecules have enough thermal energy to surmount the activation barrier. What do you think? Does that sound true or false? Sounds true. So we're not going to cross that one off. We've got to read everything else. So the reaction rates increase with temperature because as the temperature increases, the pre-exponential factor of the rate constant increases. What do you think? Let's just remember what the Arrhenius equation is. So choice B is saying that the reaction rate is going to increase because this factor gets bigger when you increase the temperature. Does this change with temperature? No. Does this one change with temperature? Yeah, there's a T in here. So B is not correct. Reaction rates increase with increasing temperature because when the temperature increases, the molecules decompose into their constituent atoms, which can then form new bonds to form the products. Does that sound anything like anything we've been talking about today? No, it doesn't. So this is the kind of multiple choice answer that's going to get the student that just really was not paying attention at all. Because it sounds good, doesn't it? It's like it sounds all fancy and scientific, and you're just like, oh, cool, that makes sense. Yeah, no, not right. So this is the correct answer. I am not going to ask you to write explanations for this, like on an exam. Partly because I hate grading answers like that, because it's so iffy, right? Well, was that correct enough? Or, sometimes it's like, okay, that's excellent, this is horrible. And then you got the ones in the middle that you're like, well, it's mostly, and mentally just draining to grade those things. So I prefer to test you on stuff like that with more of a multiple choice format, where can you recognize the correct description? Can you distinguish between correct and incorrect explanations? Okay. So A is the correct choice. I don't know why we've got our bar down here. Okay. Okay. Let's check that we didn't miss a slide there. Yeah, we did miss a slide. Okay. So we got the frequency factor, A, and the activation energy, E of A. How can we figure out what those numbers are? Well, we can measure the rate constant at different temperatures. So we keep all the concentrations and everything else the same. We run the reaction, we find the rate constant, and then we change the temperature. We run the reaction again and find the rate constant. Okay? So here's our Arrhenius equation, and if we take the natural log of both sides, we can get it into this form, which again is in the form of the equation for a line, right? Y equals mx plus b. So we graph natural log of k on the y-axis. We graph 1 over the temperature in Kelvin on the x-axis. We should get a linear graph. We can do linear regression and find the equation for the line. The slope that the computer gives us is equal to negative EA over R. And the maybe red's not the best there. I don't use blue yet. The intercept is equal to natural log of A. So this is Y. The green is the slope. This is the X value, and this is the Y intercept. Okay? Here's a little note. It's like the fine print on some web page or something. This factor A, it's in here and in here, does change a little bit with temperature. But it's pretty small, and so usually we can ignore it. So we're going to ignore that. We're going to pretend it doesn't change with temperature, because it just makes things a lot simpler, and most of the time it really doesn't matter. Okay, so we can use the Arrhenius plot to find the frequency factor and activation energy for a reaction. So we're going to have data like this, where at different temperatures, we measure the rate constant for the reaction. So here is our kinetics study, and we're supposed to find the frequency factor and the activation energy. So what do? Well, we have to do a little calculating, right? Because we can't just graph rate constant versus temperature. We need the temperature to be 1 over T, and so we would calculate that. And for the rate constant, we need the natural log of K. And so for each of these, we'll take the natural log and write down that value, and that's what we're going to graph. That sounds pretty tedious for all those numbers, doesn't it? Yeah. That's why we use Microsoft Excel. If you didn't get to that part in the experiment on Tuesday, you'll get there today, and we're going to learn how you can type in an equation here, equals 1 divided by box, and that'll calculate 1 over T for you. And then you copy that box for everything else, and it does all the calculations for you. And it doesn't make mistakes. If you do this with your finger on a calculator, you're going to screw it up occasionally, right? And that's really frustrating. Here we just say equals natural log of this box. We have our answer here. We copy that box down, and we get the natural log of everything. And then we say, okay, Excel, graph it for me. And ta-da! It makes something like this. The natural log of the rate constant versus 1 over the temperature. And this is the equation that the computer will give us, the equation for that line. That equation corresponds to natural log of K is equal to negative EA over R times 1 over the temperature plus the natural log of A. These are probably not the same colors, sorry. So negative EA over R is equal to the slope. Negative EA over R is equal to the slope, minus 1.12 times 10 to the 4. They are just equal. We don't have to do anything to it. Now, to solve for EA, we need to do a little bit of algebra. If we multiply both sides by negative R, then that negative cancels and the R cancels, and now we have EA. So the activation energy is equal to negative 1.12 times 10 to the 4th times negative 8.314 joules per mole Kelvin. So what do we get there? Nine three one 6.8. What are the units? Well, that's a good question. I'm going to show you how this works, but if it doesn't make sense, that's okay. Activation energy should have energy units, right? So in here we see joules. So this is going to be in joules, maybe something else, but joules, as opposed to kilojoules. This slope, what units does that have? Well, natural log of K has no units. The slope is the difference in Y, which has no units, divided by the difference in X that has units of 1 over K. So this, great, I've been talking with this paused for a long time. So if you need to watch this video, you might want to go watch the Monday, Wednesday version because I did not make that mistake yesterday. Anyway, here we are. So it's important to be able to look at the linear form of an equation and see how it corresponds to the equation for a line, right? And that's why I'm doing this highlighting business, right? So the stuff highlighted in blue is equal to the stuff highlighted in blue. And so you're literally just picking those two pieces and they are equal, and then you can solve for what you need. So here natural log of A is 26.8. To get rid of the natural log, we do e to the x. So A is going to be equal to e to the 26.8. And again, you can use the number solver and you don't have to remember how natural logs get undone because the computer, your calculator, which really is a computer, will do it for you. So e to the 26.8. And so A is going to be 4.3560 times 10 to the 11. Again, we're not being super picky about significant figures, so we might guess, well, let's report it with 3. So that would be 4.36 times 10 to the 11. What are the units on the activation energy? I'm sorry, not the activation energy. See, A and activation energy are go together in my mind, right? Because they both start with A. But EA is the activation energy. This is the frequency factor, which I would have given capital F, but they didn't ask me. They used that for something else. Anyway, frequency factor, what's your best guess at the units? It's the number of approaches per unit time. So it's going to be per second, or s to the minus 1. We're not going to have a lot of converting between different units. We did that to you in Chem 1A because we wanted to make sure you learn how to convert in different units. And so, we'd give you a gas law problem, and, we'd give you the volume in cubic inches or something ridiculous, and you'd have to change it. Here, for the most part, the units are going to be the same. The one part that you do have to watch out for is joules versus kilojoules, okay? And we'll see that in a question coming up. The units on the gas constant can help you. The energy is going to be in joules when we're using that gas constant in there. This one you just kind of would have to figure out, and I would not try to trick you with that on an exam. Any questions? So there's our answers. For the decomposition of the ozone reaction in example 15.7, so this is the decomposition of ozone. So we're looking at this same information. Use the results of the Arrhenius analysis to predict the rate constant at 298 Kelvin. And those are the answers that we need from the previous example. So we're looking for the rate constant at 298 Kelvin. So we could use the linear form of the Arrhenius plot to do this. So the natural log of K is equal to negative EA over RT times 1 over T plus natural log of A. Or we could use the original A times e to the negative EA over RT. You guys have a preference? Which one you want to use? The one on top? Okay, let's use the one on top. So we're going to plug these numbers that we got in there. Natural log of K, that's what we're looking for, is equal to negative activation energy, 93.1. Should always use vertical fractions so that you recognize what's in the numerator and denominator. Divided by R, 8.314 joules per mole Kelvin, times 1 over the temperature, which is 298 Kelvin, plus the natural log of A. Didn't leave enough room. Common problem, 3.6 times 10 to the 11. Are the units going to be okay? No. This is kilojoules, and that's joules. Why do we do that? Because we report these numbers in tables and talk about them, and because of their size, kilojoules per mole is a more appropriate unit. We don't have to use scientific notation, we don't have lots of zeros or anything, and so this is convenient. But this gas constant is joules. So this is a thing that you have to watch out for. I will try to trick you on an exam with this, okay? Because I know a common mistake is to do the calculation with kilojoules here and joules there and come up with a wrong answer, and I'll put that answer as one of the choices, okay? So it's not really a trick if I warn you about it, is it? We could debate that. Okay, so we need to convert this to joules. So if you were in my Chem 1A class, we did this quite a bit. So 93.1, and kilo stands for times 10 to the 3. So instead of writing kilo, I'm going to write times 10 to the 3 joules. So I substituted here. So now it's in joules. And I didn't really have to do any kind of a calculation, right? It's not proper scientific notation. Your calculator doesn't care. We can just type this in and we'll get natural log of K. So minus 93.1 times 10 to the 3rd divided by 8.314 times 1 divided by 298 I like to press the equals there just to make sure it finishes that. And then plus the natural log of 4.36 times 10 to the 11, and close the parentheses and press equals. So the natural log of k is equal to negative 1007.1 and some zeros and stuff. Did you get the same number I got? Anybody? Everybody's checking. It's a lot of stuff to punch in. I'm just going to do it again while I wait here. You got the same thing? Awesome, thank you. One thing, especially like on a test, when you're doing some complicated calculation like this, I recommend doing it on your calculator twice. If you get the same answer, that's really reassuring. If you get different answers, it means you made a mistake in at least one of them. So go for best 2 out of 3. Or go back and look at what you typed in and compare it to what you meant to type in and see if you can spot the mistake. So now to find k, we're going to do e to the both sides. So e to that whole number equals, so mine is telling me 0. What do you get? You got 0 too? And you get 64?
For the LNK.
You get 64 for the LNK. Okay. Because this is not the right answer. Okay, so I'm going to try this again. The E3 divided by 8.314 over the temperature. You got negative 10? Okay.
Yeah, me too. I got this number.
Yeah. So I must have messed up somewhere in here. Oh. Okay, I see it. Instead of adding this, I multiplied. Why? I have no idea. And so you probably did that too. Great minds think alike, right? So minus, come on, 10.776. Okay. So e to that, okay, that's looking better. 0.000020891. Let's just round it to 3 sig figs. So that's going to be 2.09 times 10 to the, we got 1, 2, 3, 4, 5. Negative 5. What are the units on the rate constant?
Second. Whatever is per second. Because there is no other units.
Well, it depends, right? So what happens here is that all those units cancel out.
But the A is still the factor.
The A is a factor, but we've got the natural log of A. And so that makes its units meaningless as well.
But if we use the other equation, doesn't the
If-
percent stay?
Well, if we go back to our data, we can see that the rate constant had units of molarity per second. It's really, I think, the only way you could know what the units are. Because the units on the rate constant are different depending on the order of the reaction, right? So let's see if we got it right. Whoops. So they got 2.07. I got 2.09. Is that a deal breaker? No. That's an uncertain digit, and a little variation there, not a big problem. Okay? So if you came up with 2.09 in your calculation and 2.07 was a choice on the exam, and that was the correct choice, I would expect you to choose that. I rarely do none of the above, but those are really, really close to each other. The reason this one is a little different is because this is done without rounding, especially this number. If you don't round that number, you get 2.07. Not rounding is better, but this is good enough. Any questions about that? I would not try to trick you by giving you 2.07 times 10 to the minus 5 and 2.09 times 10 to the 5 minus 5. I wouldn't. That's not fair. That's
And is that
it's
always
me.
the rate constant? It is not always per meter per second, right?
Pardon me? It's not always what?
Per meter per second.
Correct. The rate constant does not
Like
always have
understood.
units of per molarity per second.
Okay.
This is for the
The
second order?
Yeah.
This is for a second order reaction.
So here's the
Yeah.
same idea.
So we'll see rate constants can have different units, and that can be a little disturbing. Yeah.
Could you show the breakdown for these units in this example? I feel like
Actually, I can't. I
was
can't.
trying to.
Yeah. So he's asking for the breakdown of the units here. So let's look at this. So joules cancel with joules, moles cancel with moles, kelvins cancel with kelvins. This term is unitless. When we take the natural log of something with units, then the units become really meaningless, right? So we think of this as not having any units, and we think of that as not having any units. So it doesn't work out. That's disturbing, isn't it? Yeah. I can't explain it.
We just know that it's molar.
You would just have to know by looking at the data, you can tell, because that had rate constants in it and the units in there were given. So if that was the units of rate constant on the data, this must have the same units. Yeah. But the rate constant units don't work out with things. And it bothers me too. Yeah.
Is the frequency factor always per second or not?
Pardon me?
The frequency factor.
The frequency factor has to be per unit time, and by default that would be seconds. Yeah. You could see it expressed in something else, but if they don't say, it would be per second. Yeah. Any other questions? These are good questions. So we can also calculate the activation energy if we know the rate constant at two different temperatures. We can't get the frequency factor, but honestly, the frequency factor is not very useful. So this is called the two-point form of the Arrhenius equation, and you'll notice it bears some similarity to the linear form. We would use this when either we have limited data or we can't graph because we don't have access to that. So like on an exam, I'm not going to give you a whole table of data and make you punch it in and do that whole business. But I definitely will give you something like this. I'll give you 2 rate constants, 2 temperatures, and say calculate the activation energy. And then you plug them into this equation. So let's do an example like that. Consider the reaction between nitrogen dioxide and carbon monoxide. The rate constant at 701 Kelvin is 2.57 per molarity per second. So I'm just going to highlight those because those go together, right? And at a different temperature, at 895 Kelvin, the rate constant is 567 per molarity per second. Find the activation energy, and here they're asking for kilojoules per mole. So let's call the first one T1 and K1, and let's call the second one T2 and K2. So let's write down the equation, natural log of K2 over K1. And again, I do not expect you to be able to pull this equation out of your memory. I think it's a good idea to try to remember it, but then look at the table, because remembering the equation is not the most important thing. I remember it because I did it yesterday. So we're calling this 1, and that 1, and this is 2, and this is 2. And it's important that they match up correctly, otherwise we'll get something ridiculous. So K2 is 567, m to the minus 1, s to the minus 1, divided by 2.57, m to the minus 1, s to the minus 1. And that's negative EA, which is what we're trying to find, divided by 8.314 joules per mole Kelvin. And then we have 1 over T2, 895 Kelvin, minus 1 over T1, 701 Kelvin. Just pointing out where the 1s and 2s went. When we solve something like this, we do not try to get a common denominator to subtract those fractions. This is not math class, okay? We're just going to use the computer, right? So 1 divided by 895 minus 1 divided by 701 is going to give us the decimal answer to that, and we don't like fractions in our answers. We just want decimal numbers, okay? So you can use your solver to solve this, or you can use your brain. Does anybody want to borrow a calculator that has a solver? Yeah. So I apologize to the YouTube people. Again, I forgot to press play or record. So here we are. I don't know where I left off, but here we are. This is our answer. What are the units on this answer? Joules per mole. So here the units do come out. These units cancel out completely. Those are just gone. Here we have 1 over Kelvin, and this is 1 over Kelvin, and so those Kelvins cancel each other out. And this is units of joules per mole. If you don't see how that works, that's fine. This value is in units of joules, and so that means EA is going to be in joules. It wants kilojoules per mole. So we need to divide by 1,000, and we're going to get 145 kilojoules per mole. Any questions? Did I get the answer right? Ah. So they give 1.5 times 10 to the 2. Are those different? Not really. They rounded to 2 sig figs. Why? I don't know. If I round this to 2 sig figs, I get 150, which is 1.5 times 10 to the 2. Yeah. Okay. Okay. Now use the results from example 15.8 and the given rate constant of the reaction at either of the two temperatures to predict the rate constant for this reaction at 525. So we're going to use the numbers from this one. So we need one of these pairs. Which one do you want to use? The 701 or the 895? 701? Okay. So 701 and 2.57. So this is K, call it K1, and this is T1, and then I still have the value in my calculator. We're going to need joules per mole in the calculation, and so I'm just going to pull that number from my calculator, and I'm going to have some extra digits here. I would round to that, so that I don't end up with any rounding errors. Natural log of K2 over K1 equals negative EA over R times 1 over T2 minus 1 over T1. So they're telling us this is T2, and they want us to find the rate constant at that temperature. So K2 is going to be our variable.
Does it matter which one we choose?
It doesn't. Great question. Does it matter if we call this T1 and this T2 and this K2? No, it doesn't. Depending on how you're solving it, if you're not using the number solver, it's a little easier if you're solving for the thing in the numerator here, but you'll get the same answer. Okay, so we'll plug that in. Natural log of K2, what we're trying to find, divided by K1, which we know, is equal to negative, don't forget the negative, 1.45097 joules per mole. That was our answer from the previous problem. 8.314 joules per mole Kelvin. Temperature 2, 525 Kelvin, minus temperature 1, 701 Kelvin. Again, you can choose to use the solver or to do some algebra. there is a limitation on the number solver to how many digits you can put in. And you may run out of digits with this equation. So how can you conserve digits? Well, if you rounded this, well, actually, that's not going to help you out at all. You definitely don't want to add more digits here than you want. I don't think putting in scientific notation is not really going to help. But you want to get rid of any unnecessary parentheses. Let me know if you have trouble. So on your handouts, you have the advantage of being able to see the answer, and the book gives it as 6.13, and I got 6.10, right, if we round that. Again, that's not enough of a difference to be a problem. You could go back and just double check, like the other previous example, I put a wrong number in here, I put 9 instead of 7 or something silly like that. You go back and check, but that difference between 6.13 and 6.10 is probably how many digits in this value they used. They may have used the rounded value. If you do the calculation wrong, you're probably going to get a number that's wildly different than the correct answer. Did you get it to work?
No.
No? Yeah.
Get it.
Okay, conceptual question. Reaction A and reaction B have identical frequency factors. Reaction B has a higher activation energy. Which reaction has a greater rate constant at room temperature? Is a high activation energy going to make the reaction go faster or slower? Slower. Is rate constant bigger or smaller for slower reactions?
Bigger.
Well, the rate equals the rate constant times some stuff. So if the rate is smaller, then the rate constant will be smaller as well. So because rate A has the lower activation energy, B is the higher, A is the lower, reaction A is going to be faster. So it's going to have the greater rate constant. And those are the sorts of questions you need to be able to think through. It can be confusing, and you might need to like write some stuff down, kind of argue with yourself on paper. Questions?
So the relationship between activation energy and the rate constant is opposite?
Mm-hmm. Because it's e raised to the negative EA, so the larger that is, the smaller that term is, and the smaller the rate constant. So you can think of it in terms of the Arrhenius equation, which is great, but can be confusing. Or you can just say, well, what makes more sense? If the hump is really big, is it going to be faster or slower? It's going to be slower, right? Slow rate, small rate constant. Okay, so let's look at a frequency factor for something that has more than one reactant. Here we're looking at A plus B to make some products, and here you have an illustration. So a chemical reaction is going to happen if you have a sufficiently energetic collision between two reactant molecules. So we were talking about approaches to the activation barrier. That's equal to a collision now between the reactant molecules. They run into each other. That's the approach. The frequency factor, which is the number of, no, never mind. We haven't gotten to that yet. So, but the frequency factor is usually less than the number of collisions per second. Why? Are all of the collisions successful? No. Only the ones with enough energy are successful. If we don't have enough energy, they just bounce off of each other. And then we've got the video. So, in this video, it's like 10 minutes long, and he's going to very quickly review everything we've learned in like 2 weeks now, and talk about what we talked about today, talk about the collision model a little bit, and then he's also going to give us a preview of the rest of the chapter. It's like really fast. So if you are relying just on this to learn all of it, you'd probably have to watch it multiple times and stop and think. But a video like this can be a great thing to review once you've studied everything. So I would expect that the first half of this should make at least, you're like, okay, yeah, that sounds okay. And the second part might be like, what is he talking about? It's okay.
What can you do with a college education? Out here, you can do a lot. Go from top-rated academic.
Have you ever been to a demolition derby?
Pardon me? No. Because I made PDFs. I never even thought of that. But I can put the link where the slides are. Yeah, I'll do that, thank you. So have you ever been to a demolition derby?
Basically, a bunch of people driving cars around the field doing their best to ram into each other while protecting themselves as much as possible. The goal, of course, is to damage the other car so badly that they can't be driven anymore, and the driver of the last operational car wins. You know Crash Course Chemistry well enough to know that I probably wouldn't have mentioned this if it didn't have some relation to chemistry, so yeah, it does. Chemical reactions basically work just like this. Atoms and molecules move around their environment, occasionally ramming into each other. If they do it just right, a reaction happens between them, and if enough of them do it, the concentration of the reacting molecules will go down, while the concentration of the products goes up. Wait, but it's not as simple as it sounds. For demolition drivers or for chemicals, in both cases, a lot of the collisions that occur have very little effect on the end result. One molecule hitting another doesn't mean a reaction's going to take place. In the same way that just randomly bumping into another guy's car doesn't mean that you're going to ram him out of a derby. So, what makes a collision effective? The hit has to be hard enough, and it has to be aligned just right. The branch of chemistry that studies how these collisions affect the rate of reactions is kinetics. And if you ask me, it's just as exciting and a heck of a lot more useful than demolition derbies. If only they sold funnel cakes in chemistry class. So, if chemical reactions only work when particles bang into each other good and hard, just how hard do they have to bang into each other? Every reaction has a minimum amount of energy required to get it started. This is known as the activation energy. Molecules require this much energy to hit other molecules hard enough to break them apart and reform them in different ways. Without it, nothing will happen. It's like a hill that molecules have to get over before they can go any further. So where do they get this energy? Well, it's kinetic energy, the actual speed of the particles. So just like the cars in a demolition derby, all else being equal, the faster the particles move, the harder the collision will be. But still, no matter how hard they hit, it won't do any good if they're not hitting the right way, in the right places. Like if you keep smashing into the back of a guy's trunk, that's not going to stop his car. There's no engine back there. You can bang Velcro together all day and night, and if it's not turned the right way, it'll never stick together. Same thing with molecules. As an example, take nitric oxide, one of the byproducts of gasoline combustion, and something that you can smell quite clearly at a demolition derby. Under the right conditions, it reacts with hydrogen gas to produce nitrogen gas and water. But the molecules have to hit each other just the right way. To make N2, two NOs have to collide in such a way that the nitrogens are together, and to get H2O, a molecule of H2 has to collide with the oxygen side of an NO molecule. Just like Velcro being turned the wrong way, you can smack the N side against the H2 all day and you'll never get any water from it. Now let's say that we're having a lot of solid, effective collisions between the molecules. The reaction should hum along with no further hindrances, right? Well, yes and no. Once the energy requirements are met, the reaction will proceed, but its speed, or reaction rate, will vary wildly from super fast to super slow. So the reaction rate, that's the rate at which the concentrations of the reactants decrease, and this has to be determined experimentally. It can't be calculated from the energy change or any other thermodynamic factor. One useful way to think about the rate is a quantity called the reactions rate law. It describes the relationship between the initial concentrations of the reactants and the rate at which they react. The rate law for a reaction is written like this. The rate equals a constant K times the concentrations of each reactant raised to some power. Notice that only the reactants are used for this, not the products. The rate law for a nitric oxide reaction then ends up as K times the nitric oxide concentration raised to some power times the hydrogen concentration also raised to some power. So you're probably wondering about all those raised to some power, like what power, and you should be wondering that. The exponents in rate laws are tricky, even for professional chemists and engineers, because like I said, they can only be determined experimentally. It's kind of intense, but we can handle it. Check it out. Suppose we did the reaction a few different ways and calculated the rate for each instance. Let's say that with the first reaction, we got a rate of 0.0060 moles per liter per second. Then we repeat the reaction with the same amount of nitric oxide, but this time with twice as much hydrogen as before. And now we find that the rate of the reaction is 0.012 moles per liter per second. What does this tell us? Well, doubling the hydrogen doubled the rate, meaning that the rate and the H2 concentration change in exactly the same way. So in the rate law, this can be expressed by the concentration being raised to the power of 1. Finally, we do it one last time with the original amount of hydrogen, but twice as much NO. And this time we find that we get a rate of 0.048 moles per liter per second. Doubling the nitric oxide caused the rate to increase by 8 times, and that can be expressed in mathematical terms by cubing the concentration term. This means that the final rate law for this reaction is K times the concentration of hydrogen gas to the first power, you don't need to write out the 1 obviously, times the concentration of nitric oxide cubed. A rate law in this form is said to be of the 4th order. We get that value by adding the exponents together, 3 plus 1. There is some math that isn't hard here. That equals 4. 4th order reactions are actually quite rare. Most reactions are of the 0, 1st, or 2nd order, but in all cases it's calculated exactly as we have done here. Now if you've watched our episode on equilibrium, this formula should look familiar to you. Equilibrium expressions also use bracketed concentrations with exponents, and that's no accident. Those formulas come from these ones. A reaction is at equilibrium when its forward and reverse rates are equal, right? So if we were to find the reverse rate law for a reaction, it would take the same form as the forward one, but using the initial concentrations for the products rather than the reactants. Think of like an imaginary reaction A plus B yields C plus D. The lowercase letters represent the coefficients of the reactants and products. So forward rate law is K times the initial concentration of A raised to some power times the initial concentration of B raised to some power, and the reverse is the same, but with C and D in place of A and B. Notice that these exponents are not, however, the coefficients of the balanced equation. If we write these two terms together to show that the forward and reverse rates are equal, like an equilibrium, and solve for a single constant, we get something that looks very much like an equilibrium expression. For mathematical reasons, the exponents don't translate, but yeah, basically this is where the equilibrium equations come from. Pretty cool. But if it's that simple, why don't all reactions just go to an equilibrium state and stay there? Well, sometimes the reverse reaction isn't thermodynamically spontaneous for one reason or another. Sometimes the forward reaction is so vigorous that any reactants that might reform are immediately pushed back into products, or the products might physically separate and have little chance of colliding at all, like when products separate into solids and gases. Often though, it's just that the reverse reaction has such a high activation energy that the collisions are almost always ineffective. Because remember, most reactions don't happen instantly, boom, all at once. Instead, they happen in steps. And as with any multi-step process, the reaction can only happen as fast as the slowest step takes. And sometimes that step is very slow indeed. Since it's what controls how fast everything else can go, we call it the rate limiting or rate determining step. The slowest step is the one that has the highest activation energy. If the particles have trouble getting over that part of the energy hill, then they'll have trouble making it to the finish line, no matter how fast the other steps are. So in the case of the nitric oxide reaction we've been discussing, there are actually 3 steps. First, the nitric oxide and the H2 form water and elemental nitrogen. Then, the nitrogen combines with another molecule of NO to form N2 and elemental oxygen. Finally, that atom of oxygen combines with another molecule of H2 to form water. Here, step 2 is the slow one, and no matter how fast you take the first step, the water product can never be produced until the nitrogen gas is. Problem is, we can't always afford to wait around for reactions to happen on their own. Sometimes they need to be forced along, and that's the job of catalysts. A catalyst is a chemical that lowers the activation energy of a reaction, thereby speeding it up without actually being changed by it. Catalysts take many different forms. They can be just another chemical added to the reaction vessel, a piece of metal that's in contact with the reacting chemicals, or even a gas that's added to the environment. One of the most common and important classes of catalysts are the enzymes in living things. Without them, many of the chemical processes that our bodies must do every day to keep us alive would slow essentially to a stop. We literally could not survive without them. So there you go. In demolition derbies and in chemistry, it all comes down to how hard you can hit and how well you can aim your punches. Chemistry, surprisingly exciting, even without funnel cakes. Thanks for hanging out for this episode of Crash Course Chemistry. If you paid attention, you learned that chemical reactions depend on collisions between molecules and atoms, that the particles have to be oriented correctly when they collide, and that they have to collide with enough energy to meet the threshold for the reaction known as the activation energy. You also learned how to write rate laws and figure out their exponents and how to calculate the form or order of a rate law. You learned how rate laws are related to equilibrium expressions. And finally, you learned that chemical reactions actually happen in steps. That the slowest step determines the overall rate of the reaction, and that the reason for that comes right back around the activation energy. This episode was written by Edie Gonzalez and edited by Blake DiPastino. Our chemistry consultant is Dr. Heiko Langner, and was filmed, edited, and directed by Nicholas Jenkins. The script supervisor was Michael Aranda, who is also our sound designer, and our graphics team is Thought Cafe.
It's a great channel, Crash Course Chemistry. But all of the videos are like super fast like that. He's a high energy guy. Okay, any questions about the video? Did some of that sound familiar? And then the stuff at the end about reaction mechanisms and catalysts, we're going to do that on Tuesday. Okay, so just talking about that collision factor, the collision model, the frequency factor that we've been talking about, A, can actually be broken down into 2 different factors. There's the orientation factor and the collision frequency. So the orientation factor is the fraction of collisions that have the right orientation. So that's going to be a number between 0 and 1. And the collision frequency is the number of collisions per unit time in the ballpark of 10 to the 9 per second. We're not going to do calculations using these equations, but we do need to understand how the orientation factor contributes to the rate constant. So if we have 2 molecules that are going to react with each other, they have to bump into each other in a way that allows the necessary bonds to break and to form. So here we have 2 molecules. They each have 3 atoms, and they're going to form my favorite, NO and chlorine. If they bump like this, nothing's going to happen. If they bump like that, nothing's going to happen. Just like, the derby, if you're crashing into somebody's trunk, you're not really messing their car up, and you might actually be messing up your engine because your engine is in the front, right? It has to be the correct orientation. So the 2 chlorines in this example have to hit in order for a reaction to occur. So for this particular reaction, that orientation factor is 0.16. So it's pretty small. That means 16% of the collisions have the correct orientation. So not very large. Yeah.
So
Oops, didn't mean to do that. Oh, increase the light, I'm sorry. Yes. Okay. So if we have a small orientation factor, like 0.16 is pretty small, that means the molecules have to be aligned in a really specific way. If we have reactions between atoms, that orientation factor is going to be close to 1. Why is that? Well, atoms are spheres. One side of an atom isn't any different than the other. So two atoms colliding are always going to be in the correct orientation, right? And what's really weird is it's possible for the orientation factor to be greater than 1, which indicates that an actual collision is not necessary. Weird. We're just going to leave that there. So this is a kind of a question you should be able to answer on an exam. Which reactants do you expect to have the smallest orientation factor? So we need to be able to figure out, well, what does smallest orientation factor mean? That means a small fraction have the correct orientation, right? Smallest orientation factor. So is that going to be simple things or complicated things that are not going to get oriented very well? It's the complicated ones, right? So it's good to figure that out in your head. You're looking for the more complicated ones. Here we have 2 atoms. Well, those are going to have no problem. Here we have 2 molecules, but they're both they're 2 of the same element, right? So which end is different, the hydrogen or the hydrogen? Yeah, it's the same. But, do they align side to side or hydrogen to iodine or exactly how? This is a little more complicated than that. And here we have 2 HCl molecules, where if we get the hydrogens colliding, that might be good, but if the hydrogen collides with the chlorine, that's not good. So which is going to have the smallest orientation factor? C. Do you see?